Okay, our next hands-on activity, conducted by Dr. Nadia Smith, is a case study assessing severe weather with new caps sounding products. Nadia has over 10 years of working atmospheric remote sounding, infrared and microwave sounders with the University of Wisconsin-Madison and with NOAA. Nadia is a subject matter expert in new caps, which is a multi-instrument method combining infrared and microwave sounding information that NOAA runs operationally for SNPP, CRIS, and ATMS, and MEDOP, IASI, and AMSU. So welcome, Nadia.
Thanks for the introduction, Christy. In fact, I started my career as a scientist, switched over to satellite soundings in 2006 when I attended a direct broadcast applications workshop where Kathy was there and presented by the University of Wisconsin. And you can follow, if you go to the main page of this course and you go to the training resources, there's a link to the Direct Broadcast Applications Workshop. There's a Direct Broadcast Applications Workshop link. And you go there and you see all these workshops that the University of Wisconsin has organized and hosted all over the world. And the 2006 one in Pretoria, South Africa, was where I was an attendee, and I was in awe. So I thought that they did such a great job in explaining hyperspectral soundings that I included some of the slides used back then in my discussion today. So you'll maybe recognize some of that if you go there. But there's a lot of really great material there. So how we're going to do this exercise today is perhaps an exercise in communication more than weather analysis, because we found that the satellite sounding products are more esoteric or obscure than a picture or an image, a satellite image. Previously, what we've seen in many presentations, we saw people showing imagery, and your human eye can see that very easily, and you can relate and you understand what you're seeing. Whereas with satellite soundings, the information in there is not immediately obvious, or it looks degraded compared to these high spatial resolution imagery because it has coarse footprints. Its true value is really in this high vertical resolution. And so this is a real challenge for us to have found and nurtured a user community for satellite soundings, because there's historically been a disconnect between product and algorithm developers on the one side and the weather forecasters on the other side. And so what we have done through the Proving Ground, the JPS's Proving Ground and Risk Reduction Program, was to bring these two communities together. And we have been really successful since, for the past, say, 5 years or so. And for the latter part of my talk today, I would like to invite Dan Neatfield to join me here on the podium, and we will have a bit of a conversation to demonstrate how trying to make sense of this data in analyzing weather. Measuring the atmosphere is a very difficult task because it's this three-dimensional medium that changes constantly at multiple scales. And so to make a measurement of any one change or any one parameter, never mind all of it, and then how they interplay and affect each other is really difficult. But I feel that with satellite soundings and the NUCAPS product suite specifically, we're definitely making some inroads in trying to characterize some of the more complex atmospheric processes. So today, I will spend some time explaining what these measurements are and then highlight some case studies. But thanks to many people before me today, we've already seen how these NUCAP soundings are applied in many different types of applications. So, and then we'll have a conversation between myself and Dan. Thanks, Dan. So, what is a satellite sounding? We've had our community as satellite sounding developers. We're trying to undo decades of miscommunication. Only through the Proving Ground program did we realize the depth or the extent of the misunderstanding, because we would say things in a certain way, and then someone would understand it completely differently. And it's only when you have to use this information in decision making that you realize, oh, wait a minute, that's not what I meant. What I meant was this and this. So we've really had to redefine or reevaluate the language we use in talking about these products. So how we think about it is remote sensing is looking at something, but remote sounding is looking through something. So you're looking through the atmosphere. Ultimately, what we do then have with the remote sounding measurement is a three-dimensional measurement, where with satellite soundings, then you have a vertical profile of the atmosphere, and you have wide swaths of them, so you end up with a data cube, a cube of measurements about the atmospheric state. So that is what we have. And Mitch mentioned earlier that it's difficult to just look at a hyperspectral infrared measurement because you have thousands of channels, and even then you have 100 layers of measurements that you can have in the vertical atmospheric column. So there's a lot of data there, and to visualize it effectively it can be challenging. Anyway, so this is what we have. A sounding is a set of profile parameters that characterize the atmospheric state. This can be temperature, moisture, ozone, carbon monoxide, all the molecules that exist in the atmosphere. And together we would often use the term sounding to say the whole set of those. A satellite sounding is then a remote and indirect measurement of a vertical column of atmosphere. And I'm using these terms very specifically because that distinguishes it from a radio sound, that it's also a sounding. A radio sound is an in situ, point source measurement of a vertical line through the atmosphere. So it's important to understand the difference between these two, so that in applications, when you use it, you can make sense of these measurements. So ultimately, sounding, even though we look at it as one single profile, it really represents a column of atmosphere. So you contrast that with a radio sound that measures the points through the atmosphere as it travels up with the balloon, and you will see two very different data sets there. This is what the measurement looks like. The infrared spectrum that we measure at the top of atmosphere. This is in brightness temperature units, and what contributes to the signal at the top of atmosphere is the upwelling infrared radiation from the surface, and it's also that upwelling radiation from each layer of the atmosphere. So it's all combined in there, together with reflected downwelling and reflected solar. So this is a compound signal of the entire atmospheric state. So we then use this one single measurement and map it into profiles of distinct parameters because, oopsie, that wasn't supposed to happen, because of the fact that different molecules in the atmosphere have different spectral signatures. Those molecules, they vibrate in the atmosphere, they absorb and emit radiation, and that radiation eventually then reaches the top of atmosphere, and it's measured by the instrument, and the amount of energy that was absorbed and emitted by that molecule generates a signal, spectral signal in the infrared, and because of that, we can define what it is in the atmosphere. So here I just highlighted some specific gases. It's not all of them, but it should give you an idea the different spectral regions where these spectral signatures are. water vapor, carbon dioxide, carbon monoxide, methane, ozone, and then there are also the window channels that see all the way through to the surface. So you really can derive information. There's information in this one single spectrum from all those channels that gives you information about the energy at specific pressure levels in the atmosphere. So because of that, we can construct these profiles. So here, to really just bring home this point, is that on the left-hand side, you see this brightness temperature spectrum now turned on its side, and with different channels highlighted there in different colors. So for example, the blue dot there on the left-hand figure is sensitive to the tropopause and at 100 hexapascal. So in the center figure, you can see that blue line, and that is really the sensitivity function of that channel. So that channel contains information about that upper tropospheric, lower stratospheric region in the atmosphere, a broad layer, and because of that, we can then map it into the profile there. So it's difficult to do this without a pointer, but on the right-hand figure, then you see where the information in that channel, the blue channel, where it mapped to in that vertical profile. And that, in the vertical profile, it's really not a dot, it is that broad blue layer it's a broad layer of information that came from that one channel. And so you can follow it through and even read the temperatures off of there. So that blue dot has a temperature of about 210 Kelvin in the brightness temperature, and that then in the temperature profile you could see there 210 Kelvin in a temperature profile. And then you follow the green dot that is now the mid-troposphere, sensitivity function there. You can see the green weighting function, and then again there it is representing information in the mid-troposphere of that temperature profile. So each one of those you can map through and see where that information comes from. So that infrared spectrum contains the information that eventually that we can put together as a profile. Oh, that's true. I forgot about that. Thank you. I'll use the trackpad. Here you go. So to show you how these measurements vary throughout the atmosphere, I plotted here the different brightness temperature spectra for a cyclone, tropical cyclone, from the edge of it to the eye. And here is the clear sky spectrum on outside of the storm. You can see this here. Then the opaque cloudy region of the storm is this blue one here. You can see it's really opaque high clouds signal here. And then the eye of the storm has this spectrum here. So you can see that clear sky coming through there. So you can see there's an incredible range of values that you get from these measurements. So there's a lot of information contained in here. I'm going to walk through these slides now to really give you an idea, to really bring home this message. So here you have, at the bottom, you have a clear sky brightness temperature spectrum, this measurement, and these are the derived profiles. This is temperature, here's the humidity, and here is ozone. So humidity information comes from this spectral region here. The ozone information comes from this spectral region here. That's the ozone signal there, absorption band, and the temperature information comes from this section here and a little bit over here. So here you see what this is like. If I now introduce a cloud at this level here, at 700 hectopascal, you can see the change in this spectrum. You can see how this surface temperature here that's near 300 Kelvin, and here my surface channels are near 300 Kelvin, you can see now when I have a cloud top up at this level, how that the surface temperature now at the cloud top is down to 270 or so Kelvin, and here my brightness temperature moved down. And also water it decreased now because I'm only measuring the atmosphere above that opaque cloud. And so you can see the water signal is also lower. I'll toggle back and forth a little bit between these. So you can see there, the ozone is unaffected. Ozone signal, the strength of this absorption band is unaffected because we're not measuring ozone at that boundary layer. We're not sensitive to ozone at that boundary layer. And so if you get to clouds that incrementally go a little bit higher, you can see how that changes. Now you have a high cloud, a mid-tropospheric cloud, and you can see the temperature gradient there is a very small gradient. And there's just now the stratospheric temperature signal left there, and almost no water vapor. And then when this cloud is really high, all the temperature above that cloud top is warmer than it. So here you can see that the surface channels now contain no information there. So this really just, I'm showing these to show you that these measurements are physical, and the information in the profiles can map directly back to that spectrum. So we're not, yes, there's uncertainty in these measurements. Yes, we have to understand them, but there are physical measurements about the state of the atmosphere. One thing that is interesting to note, between a satellite sounding and a radio sound, is that a satellite sounding has these, we parameterize this spectrum into distinct profiles, but ultimately these profiles are correlated because they come from the exact same measurement. Whereas in a radio sound, you have two different sensors measuring, well, the one measures temperature and the one measures humidity, and so they are independent of each other. So you have these different differences. Here I'm showing you now what it looks like in different regions of the world. Here is a solar reflection. We can see solar reflection radiation over here, and it's a cool surface there. This is a hot surface, desert emissivity spectrum feature there, and it's nighttime because there's no solar reflection. Here is a transparent cloud, solar reflection during daytime, a cloud feature. When we see these absorption lines like that, we know that there's surface inversion. And again, this is nighttime without any reflection. Here is a cloudy, high cloud nighttime spectrum, and here is again desert daytime spectrum. So you can see how these spectra change throughout the time of day and in different regions. And so what we do, we can read these spectra like signatures. We can read them with our own eyes. That is what we read. We learn to read those based on what we know about the spectral behavior. And so what we do with our algorithms is just to automate that process where you map the information in that spectrum into the profile space. So you take it from a spectral space into profile space. So NuCAPS is really that algorithm. It's the NOAA unique combined atmospheric processing system. It runs operationally at NOAA and is also available through CSPP to run at direct broadcast stations. NuCAPS is multi-platform, so it's really an all-encompassing sounding system. It uses both infrared and microwave measurements to derive a cloud-cleared sounding, and I'll get back into that a little bit later. And we can run it on the sounder pairs on the MEDOP A and B satellites, as well as the SUMI NPP and soon NOAA 20. That means that you have multiple soundings throughout the day. So each polar orbiter platform measures the same location twice a day, one at nighttime and one during the day. And the benefit of these infrared measurements, infrared and microwave, is that you have measurement continuity throughout a 24-hour cycle. You have the same quality of information at night and at daytime. So that is quite powerful if you think about big evolving systems that you need to have a nighttime measurement, and perhaps Dan will speak a little bit more about that later. So these retrievals if you look at one of those dots, so these dots are what you typically see in an AWEBS environment, and Michael Boland introduced that to us earlier. So when you look at these dots, they should not be confused with radiosondes. They are not point source. Remember, they are volumetric measurements. So they really represents this column of air, and that profile is made up of these broad layers of information that you demonstrated earlier. So this is what you should keep in mind when you use this data in AWEBS. We have also seen what Michael Boland did was introduce the two different visualization modes in AWEBS. These are the Skew plots that forecasters use. That's their bread and butter, their coffee in the morning. And also the gridded NuCaps. And the gridded NuCaps visualization really developed because there was a need to visualize three-dimensional structures in the atmosphere. You can get a lot of information about the atmosphere from a single profile, but what if you have a feature like a cold air aloft blob that you need to know its spatial extent and its vertical extent? So how do you go about visualizing that? So then what we did was to develop this capability in AWEBS to take this swath of soundings, and instead of visualizing one profile at a time, we would slice it like this. You would visualize one pressure level at a time. So it's made up of vertical, horizontal slices through those swaths of profiles. So we found now, as is evident by all the forecaster feedback during the HWT, that both of these visualization modes have value because we need that to maximize the value of these NuCap soundings. I need to say a quick note about clouds. Well, clouds are everywhere, and an infrared radiation it's opaque clouds obstruct that. But whereas microwave information or radiation moves through clouds. So what we have is you have one measurement, the microwave data measurement that can see through the clouds, the atmosphere through the clouds, and despite the clouds, it's not sensitive to the clouds. But then you have the infrared that is obscured by the clouds. So what we do in NuCaps is to perform cloud clearing. That means that you use both, you anchor your solution to the clear sky solution in the microwave, and you remove the cloud signal from the infrared spectrum. And we can do that because, like you've seen previously, the behavior of that spectrum is proportional to the cloud height. So we can derive the cloud information from that infrared spectrum if we know the clear sky spectrum that we have in the microwave. So that's how we do it. So what we ultimately do, I'll get back to this slide, but I just want to switch to the next one. So here is what we have now. This yellow is really the footprint of NuCaps. And these gray circles here, those are the 3x3 crisp infrared footprints. So we use 9 crisp footprints to derive a clear sky infrared radiance from which we then retrieve a cloud-cleared profile. And a cloud clearing works when you have cloud contrast in your footprint. So what we have here, these are all scenarios where cloud clearing will work really well. You have cloud contrast because inside this set of 9 spectra or footprints, you have varying cloud amounts in each of those footprints. And so you can use that to linearly derive the clear sky spectrum. So if you're in AWEBS or any other visualization mode, you see a sounding over clouds, and it's a good sounding that passed QC, you can rely on the fact that it was probably an environment where there were broken clouds. And so we were able to successfully clear the clouds from our retrieval. Here are scenarios where it will not work, when you do not have a gradient of or variation of clouds in your large footprint, and all the infrared spectra really measure the same same big opaque cloud field. And under these conditions, cloud clearing will fail, and that is when our NuCAPS retrievals also fail. So when you see gaps in the data, when you visualize it as a plan view in AWEBs, those gaps are over these opaque, thick cloud fields. That is when cloud clearing does not work. So, so how do you make sense now of a cloud cleared profile? I had a forecaster ask me a very good question, and which made me stop in my tracks to think about it. He said, well, you know, I see that you have this profile in this cloud field, but where are the clouds information in your NuCAP sounding? And I said, well, we clear the clouds, so we don't have it, but that language didn't quite explain it. He's used to visualize, or he's used to radio sounds. Balloon launches, it launches and it can travel through clouds, and it measures the temperature and moisture at those points throughout. And so what you sometimes see in a radio sound is that in the environment, the temperature and moisture environment inside a cloud field. Whereas a NuCAP sounding, we remove that cloud signal from the radiance spectrum, and then when we map it into profile space, so we have that profile of the clear environment around those clouds. So how we're trying to communicate this is to say, well, yes, so here we have broken cloud fields, and we're really measuring the environment around those clouds. So this is what it will be in a nadir one. So your entire footprint remember now we're measuring a column of air, so it's not just a line like that, but it's a whole column. So there may be clouds in that column, but we're measuring the clear part of that column. That is what you have in your NuCAP sounding. And so if you have a view, if you look with a view angle too, you have your edge of swath, then you can imagine that you visualize it like this. So that column of that we measure profile really is sometimes even under those clouds. So bear that in mind when you interpret these results. This is how we treat clouds. The reason why we are doing cloud clearing is that there are very few cloud-free NuCAPS footprints. A NuCAPS footprint, the CRIS instrument measures, the footprint is about 15 kilometers at nadir, and that this yellow NuCAPS footprint is 50 kilometers. And so there are very few cloud-free scenes. So we're doing this cloud clearing to increase the yield. Global yield. If you think about all the measurements that are made, we're getting about 70% yield out of all the measurements, and that is critically important if we are to evaluate an evolving atmosphere. So this is what we have in NuCAPS. I'll stop there. There are some training modules available that Scott Lindstrom did. This is a YouTube visual presentation or online, and I thought that is actually quite good. And Eric, you mentioned that maybe Michael Boland should show you how to do that adjustment. And in this presentation also, it is shown, Scott does show how forecasters can adjust the boundary layer according to surface measurements if they want to do that. So that I would recommend that presentation. And then there's also the HWT that you've now learned about. To read through those blog posts are quite valuable because it's like a stream of thought from a forecaster. They say, oh, this didn't work well, this looked great, oh, I think this could be useful in future. So if you're interested in these products and to want to learn how forecasters are thinking about these products, those blog posts are quite a good read. So the types of parameters derived from NuCAPS, I've mentioned now temperature profiles and moisture profiles, and then we also have trace gas products, carbon monoxide, ozone, methane. Those are the profiles that we retrieve, but you can also derive a whole suite of different information from those profiles. So what forecasters typically do, we'll get more into that in the next phase of this presentation, but I'll just highlight some of them here. This is a slide by Emily Byrne, who's now the NUCAPS expert at sport. And here it just shows you what forecasters typically look at, and they use this combination of in situ observations, satellite data, and models. So what NUCAPS does is it is an observational data set that that complements the forecasting environment. Forecasters use NUCAPS to evaluate the models with, because models don't always get it right. Models can often overemphasize, or they are. Chris White told me that they're too much convection sometimes. They predict too much convection, or their mid-level moisture is not very accurate. So you have this observational data set that can then be used or compared to those models. The interesting thing about it all is that there's not one data set that solves all problems and observes everything to the highest accuracy. You have these different data sets that succeed and specifically that fail in different ways. A forecast model may fail because of convective physics but a satellite observation, a satellite sounding will fail because of clouds. So you have those, they fail in different ways, and that is important because that means that if the one fails or the one has a shortcoming, then the other one can possibly fill that gap there. Here are some of the parameters that you can derive from these profiles, and those are dew point, depression, lapse rate, total index, CAPE. There are a lot of many different parameters, and each forecaster has their own suite that they like to use. But this is just to show you that to retrieve these profiles is just almost an intermediate step. It is all the products that can be derived from these profiles where in applications where the value lies. This cold error loft that we've already seen, this is really an excellent application, because here you had this three-dimensional observation suite that could fill that data gap, and we could really then step forward and provide forecasters with this three-dimensional view of a three-dimensional feature in their atmosphere. And this is what it looks like in AWEBs. Here you can see how it's possible to visualize this data. You can visualize it as a horizontal map at a specific pressure level, or you can visualize it as a vertical cross-section along a specific, so this vertical cross-section comes from a scan line like that. So you can just move this vertical cross-section along the scan lines, and you can get a sense of the three-dimensional environment there. Or you can loop this horizontal plane through all the vertical layers to visualize that. Here are some of the feedback that forecasters gave during the 2017 evaluation. And as Eric said, we're very excited that the latest 2018 cold air loft evaluation was launched yesterday. So we'll be watching as comments come in. It's really quite interesting. So here, what we've learned is that NUCAPS observations do very, very well with this elevated temperature measurement. So a satellite sounding, we have to remember now what I meant when I said it's a remote measurement. It measures the top of atmosphere radiance, and that means it's a top-down measurement, and that signal that we saw, that spectrum, is a compound of all the absorption and emission throughout that vertical atmosphere. So it has sensitivity, different quality of sensitivity depending on the height of the atmosphere. So in the boundary layer, which is now the furthest from the satellite, if you may, it's at the bottom of the atmosphere from a satellite perspective, that's where these satellite soundings have the lowest sensitivity. So we often have the highest uncertainty in the boundary layer of these soundings. But with cold air aloft, those temperature blobs are here in the mid to upper troposphere, and so those that's where these satellite soundings have very high skill and low uncertainty. So this product can be used with confidence because of that. So other applications, we've heard Michael Fulmer talk about extratropical transition. They recently published a paper on that, so that's worth a read. Fire weather, we're really interested to explore that, and we'll be doing it within our community, Proving Ground community. And even here, what you have is, you have these measurements throughout a 24-hour cycle. So you can imagine now, if that mega fire is busy burning, it's not just the fire leading up to the weather leading up to the fire, it is how this fire changes the weather as it burns. So these mega fires burn throughout the day and night, and so here you have your infrared and microwave measurements about that environment, and these NUCAP soundings then give you that evolution really over a 24-hour cycle, and the value of that, because the imager products are not available for nighttime because there's no solar reflection. Hurricanes and cyclones, we've done a lot of work also in air quality monitoring with NUCAP's trace gas products, and we'll be looking at winter weather. And here, winter weather is where we will have to rely on our full suite of sounding products. The NUCAP's sounding products combine the infrared and microwave, but there's also the MIRS product that is microwave only, and it's possibly the microwave information that will help us evaluate winter weather the best. I would like to draw your attention to a NOAA tool that's quite useful if you're interested in comparing these observational profiles or the NUCAP's profiles to other model profiles or other observations outside of AWEBs. And this is the NPROFs. There's the link to it. It's allows you to do routine monitoring and also deep dive evaluations. You're welcome to have a look at it. You can also visualize it as a plan view at different heights in the atmosphere. So this is another tool worth exploring. I won't stay on this, but what I would like to highlight on this figure is really here the value of these polar orbiters and having a data product that runs on all the operational platforms that contain hyperspectral and microwave sounders is that depending on your latitude, you have a different number of overpasses. So here we can see in Alaska, you have a high frequency of overpasses and therefore NUCAP's soundings that you can use to evaluate evolving weather. But it's not just that, Anchorage and Oregon, and you can see now the times these observations come in and the value that they could have for your specific application. So here I would like to finish off this part of the talk and invite my colleague Dan Neatfield to the podium. We will both remain here and discuss a day in the life of a forecaster and what type of information they may want from a NUCAP's sounding. Thank you.
Great. Thanks, Nadia. I thought that material that you provided was excellent material for forecasters that are going to potentially use this to go through. And there is some really good training already that exists, but I think that can supplement it well. I just wanted to quickly say, too, I think this is kind of a neat example of an R2O and definitely an O2R project in which the developers are playing their part for sure, and I think some of the operational people are trying to play our part by just collaborating pretty closely with the development community. So that's been kind of fun for me to do over the years. I think we both learned a lot from each other. So that's kind of neat. So Nadia had asked me just to talk a little bit about, why on earth, again, would forecasters have any interest in this? And so what I wanted to do is just talk through a little bit of, put yourself in the shoes of a forecaster whose responsibility is to forecast thunderstorms. And I don't know that this has to be me talking to you. I think we can make this as interactive as we'd like. And Nadia and I are probably going to banter back and forth a little bit, but if people want to join in on this, I think that'd be great. And I guess a couple things I was thinking about, when's the most stable time of the 24-hour cycle? Typically it's right when the sun's coming up. That's right when we launch our balloons, right? So we're doing our afternoon convective forecast using data that we collected during the most stable time of the day. This doesn't maybe make a lot of sense, but that's the way we have done it, and that's the way we continue to do it. We routinely launch balloons at 12Z and 0Z, and again, for the central part of the United States, that's roughly sunrise and sunset in the summertime, the spring and summer. So we get our second balloon at 0Z. By then it's sort of too late, right? The thunderstorms have already fired up and they're off doing their thing, and a lot of times we consider that sounding contaminated because the balloon has gone up through convection or a rainy area. So at that point, again, you really can't assess the future stability or instability all that well. But so those are just giant problems with the balloon launches that we have. The other problem with that, of course, is that with the balloons is that they're spatially extremely coarse. There's, gosh, I forget how many there are in the lower 48, but I think it's on the order of 80 or so. So that's not very many balloons. There's one in Denver, and then there's one in North Platte, Nebraska, and then there's one in Omaha, Nebraska. So, there's no balloons in Iowa. Occasionally there is convection in Iowa, but there's no balloons in Iowa. So anyway, just pointing out some of the problems with that. And I guess I also want to mention that, again, maybe this is obvious to everybody, but when it comes to forecasting thunderstorms, there are really two extremely important drivers. The first one is, I would argue, the most important, and that is the thermodynamic profile. We pretty much have to know what the lapse rate and the temperature and the humidity profile through the vertical is, which will tell us if convection is going to be able to initiate at all. Once it does, how it will behave, and so forth. The mid-level lapse rates are extremely important for, again, just how strong that updraft growth will be. When it comes to hail growth, we typically look at the instability in this kind of weird layer that we consider -10 to -30 because that's the hail growth layer. So there's a lot of information that we need about the thermodynamic profile to accurately forecast thunderstorms. From the moisture profile, we really need to know that mid-level moisture, and in particular if it's going to be extremely dry or really wet. That can make a difference between a wet microburst type of a thunderstorm, which can be extremely damaging. In the southeast United States in particular, you can have a wet microburst with 90 or 100 mile an hour winds that are just as damaging as some tornadoes. So again, there's a lot we need to know about the thermodynamic profile. The other one is wind shear. That's the other big driving factor. And that plays a big role as well. But we have other tools for that. And then I guess I also want to mention that I thought Eric's quote about the auto mechanic having one wrench in the toolbox, we definitely don't have that, right? We have a lot of tools. We have a lot of different types of data. We have radar data from our standard 88Ds, but we have radar data from terminal Doppler radars. We have sounding data from aircraft. We have lots of different kinds of data from lots of different sources. And I think as forecasters, it's critical that we know what we're working with. We know what that wrench can do and can't do. Do we want to use any one? Not really. We want to use them combined. So I see NewCaps as it's a supplemental tool that supplements the other things that we have, like balloons and model data and so forth. So just a few thoughts that I have about that. And again, how important it is to assess the thermodynamic atmosphere. So then, after sunrise, of course, the atmosphere heats up. Typically, again, this is just some generic, typical, June day, and Central Plains cumulus clouds develop late morning, maybe around noon, and then typically, give or take, somewhere in that mid-afternoon, that's when the really good stuff really fires up. So that's why we try to get, if we can, an 18Z balloon. But as Eric mentioned, he's launched these things before. You know, it takes a whole person. Typically in the offices that I worked at, we would have to hold somebody over for overtime. We have to, you know, pay for the balloon and the instrumentation, the hydrogen. So that doesn't happen very often. These 18Z soundings, they're really a luxury. I guess back in my day, we'd maybe get one a month or so. And again, that's for a really big explosive day. So I think that the really critical factor is the timing of that pass around 18 or 19Z is just, you can't get a more golden time to have thermodynamic data. Even with the lower vertical resolution in the profile, you know, if we had the high resolution that we get from the balloon, that'd be great, but we don't. So we'll sort of, you know, we'll take that NUCAPS data because we have nothing else for sure. And not only do we get it at the one location, but we get it at all those dots that you see. So I think that it really, it's a critical piece of information at a critical time of the day. It's kind of how I've always thought about that. And I mentioned just the importance of the mid-level profile, and I think that we talked a little bit about, we haven't really evaluated the soundings during the overnight pass. And again, that's partly because a typical diurnal convective regime is that stuff fires up, you know, right around 3 o'clock in the afternoon. But we definitely have nocturnal convection. And that's not so much an issue of trying to see if the cap will break and that type of thing, but rather, again, it's that mid-level moisture. If we knew that for convection that's going to even maybe move from west to east, so it's already fired up to the west, but it's going to keep on rolling, what's that moisture profile like that those thunderstorms are going to encounter, say at 2 a.m.? That can really make a big difference in what we expect of that cluster of thunderstorms. So there's just kind of a handful of thoughts that I had. And again, working with this data sort of through the years and during these different convective seasons, you just kind of get used to it. You get a good feel for what you're working with, what you can expect. We've talked about those little inversions, and we'll show an example of that. That's a pretty small scale feature in the vertical. Sometimes NUCAPS doesn't pick up on it. But I know that as a forecaster. I know I know what that vertical resolution is in NUCAPS. So do I expect it to always show a small scale feature? No, I really don't. So I can take that into account. The example that I showed in my talk earlier, I actually did show where NUCAPS picked out an inversion, and that was a case in which the numerical weather prediction, the models did not show that. So sometimes we see it and sometimes we don't. It's a matter of just, again, kind of knowing your data. Did you want to go into the case at all?
Yes, thank you. That would be great. I would like to know your thoughts on NUCAPS from multiple platforms. When we think now about the NOAA 20, that NUCAPS products will soon become available, what is the value of having NUCAPS from both SUMI NPP platform and the NOAA 20 platform? I know that they will be 50 minutes apart. Does that matter? Would that be useful to you?
You know, yes, that's a great question. And one of the things that I've always thought about forecasting is it's all about the trends. You know, it's often, it's not about exactly what the data is at a certain point in time, but rather what's the trend? Is it decreasing or increasing or whatever the case is?
Speaking into the mic, please.
Sure, yeah. Is this better?
It's
Okay.
picked up by the sound.
I see. All righty. Thank you. Yeah, so it's about the trends. And having, again, it's almost like, think about if you had a balloon that was launched an hour later, you'd like to see how that changed. I think the other big issue with NUCAPS is that if we miss a few soundings because of the QC process and so forth, we have a shot at getting another one. So that's also important. And actually, yeah, having you know, more than just NPP, but MEDOP as well and so forth is all. Just increasing our temporal resolution is certainly a good thing. Yeah.
Yeah, let's get into the case and see what we can make of it.
Sure. So this was a case that was collected from this past summer, again, mid-June. That's a great time of the year to be in the Central Plains if you like thunderstorms. This was a pretty active day, and actually it's 2 days. On the left is June 16th, and then the right, June 17th. June 16th was a little bit more active in terms of tornadic reports and hail reports, and then June 17th had a little bit more in the way of wind, less tornadoes. But both pretty active days. And in this case, this was where the Storm Prediction Center, they issue these outlooks for convection and severe convection. They go up to what they call a high risk, and this is just under that. It's called a moderate risk, so definitely a expectation for a lot of severe weather in the Kansas City area, just south of Omaha. And then did you want to say anything about these passes, other than I guess this is just when the passes come through?
Yes,
for
I
the
think
different data
you've
sources?
spoken about the time, how the time these different things come in. So, and that was also highlighted by Michael.
Right.
You come into the office and perhaps see the 9:30 overpass, and it's stable then. But then you have the early afternoon coming through with the radios, the
Right.
satellite soundings.
Yes,
Yeah,
exactly.
that's okay.
Yep, and then of course, like we mentioned, there's the lovely 12Z sunrise to see how stable the air is, balloon. So we'll take it. I thought this was pretty interesting. This is actually a comparison of the 1:30 a.m. or the overnight, what I call the overnight pass, versus the early afternoon, the pass that occurs somewhere around 18 or 19 Zulu. And basically these dots are just colored by the CAPE, convective available potential energy values, and recall that's computed, from the sounding, from the level of free convection up to the equilibrium level. And on the left, there's not much there. Those values are pretty low. It's probably a little bit difficult to see the legend down there, but kind of the blues are below 1,000 for the most part, and then the green you get up to between 1,000 and say 1,500. And if you're not familiar with those numbers, you need some. That's basically, there's a pretty good correlation between the strength of the updraft and the value of the CAPE. So in a sense, you could say the higher the CAPE, the stronger the updraft. Stronger the updraft generally results in bigger hail, and it's pretty tough to get tornadoes with a weak updraft. So generally speaking, bigger numbers often correlate, at least, to more severity. I've seen numbers that are upwards around 7,000 or 8,000, but that's pretty extreme. Anything above, say, 3,000 is a pretty good instability profile. So then on the right, we actually do see that, and what a difference, right, between 1:30 a.m. and 1:30 p.m. The difference of 12 hours. We really increase our instability, or we decrease our stability, meaning the same thing, and we now are seeing some purples there, especially from Kansas down into Oklahoma and Texas. So those are values above 3,500. So those are really strong values of convective available potential energy.
I have a question for you about that. What we've seen is that our satellite soundings, they have a lower vertical resolution than a radio sound, and they also have the low sensitivity and a high uncertainty in the boundary layer. And often what forecasters see is, when compared to surface observations, that temperature profile, its lowest value is lower than the actual surface temperature. So when we do derive CAPE, that takes into consideration that boundary layer, we see that the CAPE values in a satellite sounding is always quite a bit lower than in a radio sound. And it reminded me of what you said. As a forecaster, you're interested in trends. And so there's a spatial gradient, and that's a trend in differences. Could these values of CAPE, even though they're not absolutely accurate, could their trends be valuable? Is that a useful way of interpreting that data?
That's a great way to interpret the data. A lot of times you're essentially looking for maxima or minima in the data. Getting to a more unstable environment or a more stable environment, the magnitude of the values they could be important, but they're not everything. So if there's a little bit of question in the accuracy of the values themselves, again, the trend, a lot of times you think of, I've got a storm here and it's moving to the east. And my question is that environment that it's moving into, is it more stable or more unstable? And so it really is a spatial trend in that regard. Yeah.
Okay.
Yep. Another interesting point about what Nadia said is that we did identify pretty early on that surface temperature and surface dew point, those are pretty critical values, especially if you want to compute a value of CAPE. So I think Michael Bolin talked about this experimental correction for the boundary layer that we've been working on that for a while, and I think that there's some promise with that, and I think that there's a lot of value in doing that. So I think that'll help with that. The other important point, and it's actually on one of these slides that you had way back here. I don't know if I should go all the way back or not, but yeah, it's down here in the lower right where it says 850 millibar computed CAPE. The way we compute CAPE is, again, we take the surface. Essentially, it's sort of partial theory, and you take some air that's at the ground level, and you look at its temperature and its dew point. And then from there, you compute the LFC. Well, that's assuming that the bubble of air that's going to eventually become the updraft started at the ground. And that generally isn't so much how it works. It's not this little bubble of air that's right here at the ground that rises. It's usually something that's several thousand feet deep. That's the bubble of air that rises up. So we call that like a mixed layer or a mean layer CAPE. And in some cases, you can just say, I'm going to start my bubble of air higher up, say at 850 millibars, and then compute that level of free convection and then the equilibrium level. And that is what was done here. So we call that the 850 millibar computed CAPE. What's great about that is that, again, it's a little bit more representative of the mid-afternoon atmosphere, and it also helps with that surface problem that we have on the new cap sounding. So in a way, again, if a forecaster is using this, he or she would know that surface temperature and surface dew point might not be super accurate, and that might be a good time to compute your CAPE value from a higher point in the atmosphere, like 850 millibars. So I think that's a good practice, doing what was done here.
Yeah, I'm seeing almost running out of time here, but I would like you to discuss that one QT.
Yep, that's a great point. I'll move ahead to that. So we did look at the increase in CAPE values here. This is showing really the similar, same type of parameter, except for this is lapse rate, change of temperature with height, and on the left is that mid-morning pass, or early morning pass rather, I think, 1 or 2 a.m., and then on the right is that early afternoon, and you can see it increase quite a bit like you'd expect. Okay, these are some soundings that were looked at from that day, and a little tough to see the map background there, but this is pointing to an area in roughly central Kansas. And on the right, we have Skew T's. Nadia's getting her good knowledge of Skew T's lately. And these different colors mean different things. The new cap sounding is the red, correct? And the actual balloon sounding is in blue. And then the green, or rather the purple, is the GFS model sounding. So we thought this was interesting in that the first thing that I noticed is that there is an inversion here. Right down here, if I can get my mouse to work right there. And that's an important feature. That it basically means that there's a little, what we call a capping inversion, that sort of hold the thunderstorm activity down. And we didn't see that in new caps. So again, this is opposite of what I showed in my talk. This is a little more common where, again, that's a pretty small scale feature in the vertical, and they don't always show up too well. But the other thing that we noticed about this particular sounding that was really interesting is that again, the red line matches the blue line on the moisture profile, especially the trend of decreasing here, and then it does pick up that sort of mid to upper level moisture pocket right there fairly well. And then take a look at the purple model sounding from the GFF, and it actually didn't show that dry air pocket at all. That's from 700 millibars up to 500 millibars. Again, that's a really critical mid-layer. And so this is a case where the new cap sounding was actually more accurate than the GFS sounding for that. We also see that trend higher up above 300 millibars where the balloon showed a quite dry area, and the model was quite moist up there, and the new cap sounding was sort of in between. But it goes to show you again, not all the tools always agree. And then we just step through a couple different locations here. This is a little bit further south, and then further south yet. And again, you can just sort of see there's definitely some similarities, especially in this case here, the three different lines, so to speak, all look fairly similar. And did you want to?
Yes, thank you. Thank you. This is great.
Yep. This was
Yeah, I think we're just about on time here. So I would just leave you here with some things to think about with new caps, and you can see here that that it takes interpretation, and it takes people to know the data, to use the data well. And thank you, Dan, for that. I think we're all still learning, and it's certainly a very productive partnership between developers and forecasters. So thank you for that, and we'll have a HWT in 2018, and we'll look forward to that this year. And also a winter storm evaluation in the fall. So we're having not just pre-convective environment studies, but also other types of weather events. So thank you. Thanks, Christy.
Thank you, Nadia. And Dan.